Alright, in this tutorial now we're going to deal with determining the rate law, but now we have an initial fast step. So we're not spending as much time as we were before, initially within a particular step. So what we need in order to be able to figure out the rate law or something like this is that we need the slow step just like before, because that is going to still be our rate determining step. But now you'll notice that this mechanism like this is going to be happening at equilibrium, and so you need that equilibrium step as well to be able to figure this out. So the rate laws for the slow step and for the equilibrium step will basically be combined together to be able to figure out the overall rate law. Rate constants, the k's within each one will combine together, and they'll form this overall rate constant, which you'll see in your final rate law expression. So let's try doing something like this. So if you look at this mechanism, you'll notice that very first step you have a fast step and it's happening at equilibrium, and then you'll notice that your next step is a slow step. So again, you need to take both into account, but what you can do with the equilibrium step is actually set it equal to each other, set the products equal to the reactants. And if you do that, you'll have the concentration of N2O2 equal to the concentration of NO, which is squared. And basically what I just did was set both rate laws equal to each other. I just didn't show it all the way. So that would be for your equilibrium step. Now if you were to take the rate law for your slow step, which is your rate determining step, it'd be rate equals K times N2O2 times H2. But again, because you had equilibrium taking place, you can't just look at this rate law and have it be the overall reaction. You have to take that first initial step into consideration. And to do that, we're just going to combine these two together. Whereas if you look at this one right here, you'll notice that N2O2 equals NO squared. So what you can basically do is put that in for that, substitute it in for that particular value, so that your overall rate law is actually going to be rate equals K times NO squared H2. And again, basically all I did was take the N2O2 that was in this rate equation and substitute it with that value. So let's try another type of example. Again, if you were to look at this, you'll notice that you have an initial fast step that's at equilibrium, and then you have a slow step as well. First thing is to go and just figure out what your the rate law, the expression is going to be that you can go and then substitute into your slow step. So it's just basically going to be, you have NO3 and it's going to be equal to the NO and the O2. Just get rid of the plus sign. So now do out your rate law for your slow step. So rate equals K times NO3 and NO. And now you'll notice that you have an NO3 here and you have an NO3 there. So basically just take all this, which is equal to NO3, and plug it in there, so that you now end up with a rate law of rate equals K. Once you substitute that in, you have an NO here, but then you also have an NO within the initial reaction, so it would become NO squared, and then you'd have O2. And that would be your rate law for this mechanism.